Good morning, afternoon, evening, and welcome to our today's webinar, which is hosted by Hexagon in collaboration with our long-standing partner and valued customer for over a decade, SABIC Specialty. My name is Shaumik Chakravarti, and I'll be your moderator today. Uh, we are thrilled to have you all join us from across the world and what promises to be an insightful deep dive into advanced material engineering. So our topic today is unlock superior predictability with validated Digimat material cards, a deep dive with SABIC. In this session, we are going to explore how SABIC's innovative approaches to material validation and simulation is revolutionizing the predictability in field grades. This is from foundational concepts to real world applications. If you're an engineer, if you are a researcher or an industry professional, you'll get you gain a lot of practical knowledge on overcoming very common challenges and also leveraging tools like Digimat for enhanced performance. Now, this webinar is tailored for professionals in industry like electronics, mobility, and infrastructure, where high performance materials are quite critical. So whether you're working in consumer electronics or producing, let's say, cutting edge appliances, whether you're working in EV battery, crashworthiness protection, or in electric vehicles, if you're in aerospace that are designing semi-structural components, if you are in infrastructure applications such as pumps, solar frames, radomes, um, these materials are going to deliver an exceptional value. So you can expect enhanced properties like higher modulus, dimensional stability, thin wall molding, high temperature resistance, and superior weatherability. And that is a differentiation factor, where you can really imbibe a lot of innovation in your designs. Now, for all those people who know us, you can also leverage high quality Digimat cards. If you're simulation engineers, you can run structural analysis like static, failure, impact, creep, fatigue, and NVH with an unmatched level of confidence. Now, this will eventually result in most optimized parts that save a lot of weight and raw material costs as well. So for today's session, to give you a quick overview of our agenda, we'll start with an introduction to SABIC, including the advantages and challenges of field grades presented by Mr. Subhranshu Mohapatra. Then Dr. Vamshi is going to discuss about the plaque geometry selection, molding, specimen preparation, and recent learnings on aging and thickness studies. Next, Sebastian will cover CT scanning for fiber orientation measurement. Dr. Prasad Dasappa will follow with material card selection, including recent improvements in fatigue modeling. Dr. Vanchi will return for a specimen level validation, and Eric Stam will handle application level validations as well. Now, finally, Subhranshu will wrap up with details on availability of SABIC Material Finder and Digimat Library. And today we have an exceptional lineup of experts joining us today, and they bring a wealth of global experience from SABIC's team in India and Netherlands. Allow me to introduce them briefly. Mr. Subhranshu Mohapatra is a chief scientist in global application technology at SABIC Specialties. He's based out of India, and with his extensive expertise, he's going to kick off the session and also close the session. Dr. Vamshi is a senior scientist in global application technology at SABIC Specialties. He's also based in India and will share insights on preparation and validation processes. Dr. Prasad Dasappa serves as a lead scientist in global application technology at SABIC Specialties in India, focusing on material card innovations. Sebastian is a lead scientist in analytical science at SABIC Corporate Technology and Innovation, based in Netherlands, specialization in advanced measurement techniques. And Eric Stam, test technician in global application technology at SABIC Specialties in Netherlands. He will guide us through the application level validation. Before we dive in, a very quick housekeeping notes. This webinar is being recorded and will be available on demand shortly after. Feel free to submit questions via the Q&A chat throughout the session. We will try to address as many questions as we can during our dedicated Q&A session at the end. So without further ado, let's get started. Subhranshu, the floor is yours for the introduction to SABIC and the world of field grades. Take it away.
Thank you, Soumik. Hello, everyone. Good morning, good afternoon, good evening to all of you. My name is Subhranshu Mohapatra. I'm the Chief Scientist at the Global Application Technology based out of Bangalore, India. It's my pleasure and the pleasure of my team to welcome you all to this interesting webinar. Before we start on the today's topic, we'd like to give a very brief introduction about SABIC. SABIC is based out of Riyadh, Saudi Arabia. We are almost a 50-year-old company having close to 30,000 employees around the world, serving 140 plus countries worldwide. We are a very innovative company having more than 11,000 patents and 20 technology and innovation centers. Today, we are streaming live from 2 such technology and innovation centers in India and Netherlands. In SABIC, we have 4 main business verticals: chemicals, polymers, specialties, and agri-nutrients. We are from the specialties vertical, where we deal with specialty engineered thermoplastics, specialty compounds, advanced composites, additive manufacturing, and thermosets and additives. In specialties, our key offerings include Ultem and Extem high-heat resins, Ultem sheet, Noril resins, LNP compounds, as well as our extensive experience in application development and prototyping. The key industries that we serve include automotive, consumer products, electrical and electronics, as well as hygiene and healthcare. Now, with this brief introduction, let's deep dive into today's technical topic. Today, we are going to talk about fiber-filled thermoplastics. Now, fiber-filled thermoplastics are used widely in many applications in the areas where the neat polymers cannot provide the required properties. This is achieved by having fillers such as glass fibers or carbon fibers to improve properties such as the structural stiffness and strength of the material. Now, these materials are used widely in many applications, whether it's automotive, ignition coils, or maybe in the the impeller for the water pump that you see at my hand here. Now, as much as we like to use this structural thermoplastics, fiber-filled thermoplastics, they also bring their own challenges in design and simulation. For example, if you see this slide in the chart that is there in the square graph, then you see that the metal properties actually vary within the part as a function of fiber orientation. If you see the red squares, that they denote the properties at different locations. Why this property change? Because the fiber orientation keep changing at different points in the application. So that's why the metal properties also keep changing. So in this case, if we use the property that is there in the technical data sheet that you see on the top right corner, which is the blue rectangle, then we'll be overestimating or taking the stiffness and strength. So that will lead to field failures. So to avoid this scenario, what many designers in the industry do is to use what we call as the quasi-isotropic metal property that is there in the blue circle. Now, this is little better, that brings conservatism to the design, but then we are not really doing the optimal design. We are not taking care of the material that is there in our hand in an optimal fashion. This can be explained little better by this slide. This slide, what we show is that in this kind of applications and materials, if you are taking the technical dataset value, for example, for tensile scenarios, then you will be overestimating the stiffness or strength by 2x. And similarly, For the fatigue case, the time to failure will be overestimated by 100 times, and the time to failure for creep will be overestimated by 400 times. So this really shows that we cannot use the technical dataset values will be way off. And similarly, what I told in the last slide, if you use the quasi-isotropic properties, the design will not be optimal. So that really brings to the point that we should be using anisotropic simulation. Now, how do we use the anisotropic simulation? In this case, it will require us to really couple a processing simulation and then performance simulation. Now, the processing simulation, for example, if you are using injection molding as a process, then we have to carry out injection molding simulation, such as in tools such as MoldFlow and MoldX 3D, where we can derive the microstructure such as fiber orientations. And once we get the fiber orientations, then we can use the power of tools such as Digimat to assign the local properties at various points in the application. And once we have the local properties assigned, then we can do a full anisotropic simulation using tools such as LS-DYNA and Abacus, and that's how we do the full anisotropic simulation. And this simulation is actually can be divided into 5 distinct steps, and that's how we are going to take our session today. As a first step, we have to do very extensive material testing and characterization, and that's what my colleague Vamsi from India will take you through. And then it will require us to do a microstructure determination to know what are the fiber orientation in actual part. And that's where the expertise from Sebastian, he will take us through that from Netherlands. And then once we have that, we need to do the anisotropic modeling. And today, my colleague Prasad Dasappa from India, he will take this through for an advanced case of fatigue scenario. And then once we have the detailed Digimat material card ready, then we in SABIC go through an extensive range of validation. The first stage, we go through a specimen level validation, which again Vamsi will take you through. And finally, we also do an application level validation, which our expert from Netherlands, Eric Stam, will take you through to show how carefully, how detailed and in depth we go to make sure the cards that you get are trustworthy and accurate, and you can really rely on us. With this, I will hand over to Vamsi to take you through to the next section on metal testing.
Thank you, Subhranshu. With this note, let's begin by looking at what all it takes to characterize the anisotropic properties of fiber-filled thermoplastics. The whole process begins by injection molding in a shear plaque. A shear plaque is nothing but a flat plaque, a 2D geometry with a gate at one end. With this, we fill the part, and towards the end of the fill, we expect aligned fiber orientations in the direction of the flow. And this is the first step in the process. There are different plaque geometries that different labs follow, as you can expect, right? So you'll see different geometries that I show on the screen. What at SABIC we do is to make sure that we study the anisotropy in any of these plaque geometries and ensure that at the locations where we cut the specimens and test the properties, the fiber alignment is well defined in the flow direction. That's the first step. Now let's take a look at how and what are the measures we need to take while carefully injection molding such shear plaques. This is our injection molding shear plaque that you can see here, which is with a cold runner. Now, typically for establishing good anisotropy in such a shear plaque, we need to fill it as slow as possible. And while setting the process parameters during injection molding, make sure to follow the recommendations set out on the TDS. And once the injection molding is completed, make sure that across shot to shot, there is consistency and the part is free of defects so that we do not introduce any other artifacts. Once we have the plaque, we then take it to mill specimens out of these plaques. And these specimen geometries could be ISO type 3 or it could be ISO type 1B depending on the size of the plaque. We first degate the part and then mount it in our fixture. The process parameters for machining have been optimized to carefully reduce the variability across tests. This ensures that you're only testing the material behavior and not artifacts for machining. And in this way, we machine or mill out specimens in 3 different directions typically. The 0 degree, which is in the direction of the flow, 90 degree, which is perpendicular to the flow, and at a 45 degree or a 30 degree, depending on the test. Once we have machined these plaques, we then machine these specimens, we take them to testing. Here we can see us carrying out a tensile testing on our UTM, and typically we make sure that we have the gauge length captured using an extensometer, the extension in the gauge length captured using an extensometer all the way till failure. And not only the stress versus strain, we also try to capture additional information such as the crosshead movement and the reaction forces experienced by the load cell. With this, let us take a look at, apart from tensile testing, what else do we need to characterize in order to fully understand the behavior of fiber field thermoplastics. So as you can see in the graph, when you take a real world example part like this, different regions in the part can have different loading states. Some of the regions could be in a state of shear, some of the regions could be in a state of compression. So we need to understand the behavior as a function of orientation as well as a function of the type of loading. And that again, we use specific geometries and test standards to characterize them as you see here. Once you have done this careful investigation, we then go into more advanced sensitivities. And one such example is in the case of a drop or in the case of a high-speed impact, where let us say you have a bumper cross-car beam or a bumper beam which is reinforced with a thermoplastic material. And when it is subjected to an impact load, then different regions in the part are experiencing different rates of loading. And the behavior of the material at different rates is different. You become more stiffer and more brittle at higher strain rates. And this is again a function of fiber orientation. So at least at 3 different orientations and 5 to 6 different strain rates, we need to characterize this behavior. And we do it for some of our high promoted grades. Apart from this, on top of all of these, you also need to consider the environment at which these components are going to be used in. And if the temperature is varying, it could be subjected to -30 operating temperature or even +85 or any other temperature, then you need to also test all of these tests at those temperatures as well. So this is the kind of detailed data that you would need to fully characterize and understand the behavior of fiber filled polymers before we go into the next step. Now, before I hand it over to Sebastian to take us through the microstructure and how he characterizes it, let me take you through a few other sensitivities that at SABIC we carefully consider. One such sensitivity is, today say for instance, I have a test campaign where I did 10 different tests and I used 600 plaques or 500 plaques to finish testing. 1 year later, a customer requests another different conditions to be tested. So we need to again injection mold and go through this whole process that I showed. Now, how are we confident that the anisotropy in the part is the same? So we carefully took and characterized the microstructure of plaques molded years apart, and we find them to be consistent in their anisotropy as long as the process conditions remain same. And the other sensitivity we consider and we need to carefully model is the effect of thickness. In a real world part, different regions can have very different part thicknesses, very thin sections to thicker sections, depending on the stiffness you want to establish. And in order to account for how the fiber orientation changes with thickness, we need to injection mold shear plaques of different thicknesses, study their fiber orientation, and model them as well. And what you see on this page here shows that in thinner sections, you can expect highly aligned fibers in the direction of flow versus thicker sections. With this brief background and our testing methodology, I'll hand it over to Sebastian, who will take us through computational tomography techniques to characterize the microstructure at these parts. Over.
Thank you very much, Vamsi. The computed tomography is an imaging technique which allows to acquire images in 3D and therefore characterize and determine the internal structure of samples. As such, it is perfectly suited for the characterization of the fiber orientation. 2D technique can be used to characterize the orientation of fibers, but they give approximated results. Ideally, to provide accurate quantitative data, computed tomography is extremely suitable. Computed tomography consists of two work streams. First, the image acquisition, and the second step, some computing to reconstruct the volumetric information. The image acquisition is performed with an X-ray scanner. It's contain an X-ray source, which is focused on the collimator to create a cone-shaped beam, which then gonna irradiate the sample, and the image is acquired with a detector located at the opposite of the source compared to the sample. The contrast which is generated is therefore depending on the attenuation of the X-ray inside the material, and the attenuation is stronger as the material is heavy. Glass fiber have a much higher density as compared to polymer. They will attenuate much more strongly in the X-ray and then create a contrast. Another part of the component of the system is a filter weld. This allows us to adjust the energy of the X-ray and optimize the contrast. We're going to use different energy if we want to image glass fiber in a polymer or carbon fiber in a polymer. Another important parameter is the resolution. In the system we have, the resolution can be adjusted by changing the distance between the source and the sample, which is going to bring some constraint in the sample size. For glass fiber, typically, I'm using a resolution of 3 micrometers, and this is typically the size of the sample that I'm using. I will now show you a bit more on the image acquisition itself. In order to reconstruct the sample and get the third dimension in the analysis, we are imaging the sample at different angle and capture different projection at different position. This is typically a scan which is performed. The sample is rotated. We have the third dimension information on those projection, and therefore we can provide volumetric three-dimensional information. Such an image is not really comprehensive, so we have additional steps to reconstruct the third dimension and generate a data set which consists of a slice of X horizontal plane, and the vertical direction is given by different frames. This is an example of a reconstructed data. The bright spot corresponds to the individual glass fiber, and we can see already that they present different orientation in the core of the sample as compared to the surface of the sample. This can be further quantitatively characterized to support the engineering team and provide some data point to validate the simulation. Using a 3D image analysis software, I can detect the individual fibers and track the center line of each of the fiber along the length, as well as measure the local orientation of the fiber. This can be represented in 3D in a color-coded images where red color shows strong orientation, blue color low orientation. We can clearly see on this image that the fiber are strongly oriented along the flow close to the surface, whereas they are oriented perpendicular or more perpendicular to the flow in the core of the matter. The local orientation of each individual fiber is not extremely useful to as an input for the predictive engineering. In order to provide some representative data, I average the orientation, the local orientation of each fiber on different slices and provide the average orientation of the fiber along the thickness of the samples. This is then used for the simulation, and Prasad will walk through the fatigue modeling.
Thanks, Sebastian, for that demonstration on CT scanning. Over the next 5 minutes or so, I will take you through some of the anisotropic models, specifically the fatigue aspects of fiber-filled materials. Now, first of all, what is fatigue? Fatigue is the reduction in the material properties when it is subjected to fluctuating or cyclic stresses. Typically, to obtain data for design and simulations, we perform fatigue tests such as this on dog bone shaped specimens to apply cyclic loads on this dog bone shaped specimens to obtain the fatigue data. Data is typically generated at an R ratio of 0.1 and a frequency of about 5 Hertz. The final outcome of this test is basically the stress versus cycles to failure as shown in the graph here. Now let's take a look at why anisotropy is very important when it comes to fatigue in fiber-filled materials. Now shown here is a graph or a fatigue data for specimens that have been cut from plaques in 3 different directions, 0, 45, and 90. As with the tensile bars, we see that the fatigue properties in the 0-degree orientation provides the highest performance, while that at 90-degree orientation provides the lowest performance. For example, let's take 30 MPa as marked in the graph here. At 30 MPa, the cycles to failure at 90-degree orientation is about 1,000, while that at the 0-degree orientation is about 100,000. So for this particular material that you see on the graph here, the variation is about a factor of 100 when orientation is accounted for. Hence, considering anisotropy in the fatigue models is very, very important. At our labs in Bangalore, we follow the ASTM D7791 standard to perform our fatigue tests. We start the fatigue test at around 60 to 70% of the ultimate stress. And for each condition, we perform tests at least 4 stress levels. And each of these 4 stress levels, we conduct 3 repeats to get an idea of the variability in the data. Now, we typically try to hit 1 million cycles to failure. Now, the outcome of this test is shown in the graph here. This characterization is good for general characterization of the fatigue properties of a material. As you can see, the data points are quite coarse, and this results in inaccuracies during modeling. Hence, we have been looking at an alternate marching method. This is based on the suggestion from Hexagon, where we conduct fatigue tests at equispaced cycles to failure or equispaced stresses until we hit 1 million cycles. Now, here the principle is instead of the repeats, we perform tests at finer increments of stresses or cycles to failure. The result is, as you can see here, better resolution in the data and hence better fits to the data that you see. Along with that, in order to obtain a idea of the variability in the data, we perform repeats at 1 or 2 stress levels in order to get the idea on the variability of the data. So overall, this method helps us getting better resolution data and better models. Now that you have seen how to obtain the test data, let's take a look at the models. Now, once we perform the tensile tests as explained by Vamshi and the microscopy information as explained by Sebastian, we can combine these two data in Digimat MX to obtain elastic plastic material cards. Now, you can add additional effects such as temperature, strain rate by performing additional tests, and that's on the tensile test. So you basically get elastic plastic or thermoelastoplastic material cards or viscoelastic viscoplastic cards, depending on the type of test that you perform. In order to capture fatigue, you have to capture at least fatigue data at 3 orientations, just like with the tensile orientation, 0, 45, and 90. In order to further improve the accuracy of the model, you could perform additional tests at various R ratios in order to capture mean stress sensitivity in the model. This results in a better quality fatigue data. So now that you have looked at both generating the data, fitting them into the models, let's take a look at some of the models that are available for SABIC materials. Here is a list of all the materials that we have. Shown in blue are the ones that have been added in 2023 and hence will be only available after Digimat 2023. For most of these grades, we have data available, the thermoelastic plastic material models available for these materials. Along with this, we have also been working on generating additional creep and fatigue data for many of these grades and should be available soon. So now that we have seen the testing, the modeling, and what data is available for SABIC's materials, Vamshi will take you through some of the specimen level validations that we perform before the models are provided to you. Over to you, Vamshi.
Thank you, Prasad. With this, we got an idea of all the data generation techniques that we follow, as well as the modeling efforts. Now, before we give these models to you, in order to enhance the trust in these material models, we go the extra mile. We also perform validations. Now, as Subhanshu explained, there are a couple of steps involved in the whole anisotropic modeling workflow. And if you recall, the first step in the modeling is to predict fiber orientations in the real world parts. Now, before we jump and do that on real parts, we need to calibrate these fiber orientation prediction models built into these processing tools, such as MoldFlow or MoldX 3D, so that for the given material, the prediction is accurate. And how do we do this? We take the same plaque that you saw that we injection mold. We take the same parameters that we have used to injection mold this plaque and replicate this whole scenario, including the mold design, in our processing tool. When we have done all of this, we then predict a fiber orientation. In the initial stage, it would look as top. The blue line denotes the experimentally observed orientation at the end of fill location that was measured by Sebastian in the lab. Now, there's a big gap. In order to validate or in order to calibrate the fiber orientation prediction models, we then tweak the constants in this model to better match the experimentally observed fiber orientation. So this is the first step. Apart from this, we also look at sensitivities that come from the meshing itself. What we have observed is you need to have a sufficiently fine mesh in order to capture the skin core effect, and also sufficient number of layers to the thickness to accurately predict the randomness that comes in the core part, in the center part. And once we have done this, we go to the next step, which is the structural validation. Now, we have done tensile testing with a certain specimen geometry. We take the same specimen geometry and then we use a structured mapped mesh in FE solver to create a structural FE mesh. And using tools such as Digimat map, we can then align the fibers in the specimen in the same orientation in the real part, similar to how we have cut them. And then we do it at 0 degree, let's say at 45 degree and 90 degree. We create the same orientations in this mapping and map the fiber orientation from the structural mesh from the molding or the simulation mesh to the structural mesh. Now this mapping is completed. You have the fiber orientations in the specimen geometry. Then we apply the structural boundary conditions. Now, in the structural boundary conditions, there are two things we do. One, we constrain one side of the specimen, and on the other side, we apply prescribed displacement. And this prescribed displacement is similar to the way we perform the test. So we take either the cross-head movement extracted from the machine when you're doing this test, and we input it in the solver, or we use virtual extensometer to measure the end of radii displacements and input it in the solver. And once we do this, we measure a couple of outputs. We measure the reaction force, and we also characterize the strain occurring at node sets at the end of the parallel region, which is the gauge region. And these are compared against, again, experimentally extracted results. And we do this not just at one condition, but at all the conditions at which we create these Digimat models. And in the case you see here, this is the implicit validation done in Abacus implicit solver for 6 different strain rates. And we see that all of these models accurately predict, or fairly accurately predict, what we observed experimentally, with a little bit higher variation at higher strain rates, which is expected. Now that we gained confidence that at a coupon level or a specimen level, we are establishing good correlation of the models and the experiments, we will move on to what we do at the next level. We will take a look at the experiment application level validation from Eric. Over to you, Eric.
Yeah, thank you, Vamsi, and welcome to the SABIC Water Management Center of Excellence in the Netherlands. In this laboratory, we can perform various validations on various samples, internal samples, and of course on the application itself. And we do the validation on the application because we want to determine whether the performance of the end application is in line with the predictions we have made before. Well, let's show one of a typical application which is used in water management. This is called a hydro block, which is part of a central heating system. And this consists of 2 flow blocks. And I will show you one flow block now. You can see that's a very complex part. This part is injected from one side, which means that the fibers are orientated in all different directions. And because it's in hollow shape, so you have the channels, it means also that you will have various weld lines on different locations, and this all together determines the end performance or the performance of the application in total. So yeah, that we need to validate here. But of course, we have also internal samples which mimic a part of what we see in the real application. So let's have a look on that. Well, first of all, if you look on the tensile bar and you have glass reinforced materials, then you know if you inject it, then the fibers are orientated nicely in this direction. If you then do a tensile test, that means that you get the optimal strength. So, and this is of course, like I showed you before, in the real application, you will have the fibers in different directions, not always in this direction. And also with this test, you will have only uniaxial stresses, which also is not the case in the real application. So for that purpose, we have different samples in-house. The first one I want to show you is a top-gated pressure vessel. Again, it's injected molded from this side, so the fibers are orientated nicely in this direction. If you then fill this with water and pressurize, then the stresses are perpendicular to the orientation of the fibers, which means that you do not get the optimal strength as seen in the tensile bar. It will be much lower, so that's something which you also see in the application. What we also have is a pressure vessel which is injection molded from the side. And we do this because you generate a weld line. That's a weak spot in many cases for materials in the application. But in this case, because we mold it from the side, it means that the fibers are orientated more in a favorable direction, so also giving more strength compared to the top-gated sample. And last but not least, what I want to show you is that we have internally a solid-state water meter body, and this we try to close the gap of what we see in the real application. So this is injected from the side, and the other side you will have weld lines, actually 3 in total, and the fibers are also in different directions. So now let's have a look on the validation test we perform in this lab. The first thing what we do is actually look on the hydrolytic stability of materials. For that, we use tensile bars. We expose them in hot water for 1 or 2 years, and then we determine whether the material can withstand the water. It sounds very simple, but I can tell you there are a lot of materials which cannot withstand hot water over a long period of time. And only those materials which are good candidates, so they can resist for a long time water. We continue with more advanced testing. And the first test we do on the application, or an example I will show you is an internal sample, is a burst test. And in this case, burst test means that you connect this to a water system. Inside is filled, and you increase the pressure with the pressure ramp, constant pressure rate, until the material of the sample fills. And so it can be this sample, but it can also be an application. We will now see a video of this recorded with a high-speed video of a sample which is Noryl glass reinforced material. Okay, it's nice to understand the burst pressure, but it only gives you information about the short-term strength of the material of the application. So you have to think you have peak stress in your system, but it doesn't give you the answer for the long-term performance. So many of our customers require fatigue testing, and the problem with fatigue testing is that each customer is having different ideas and different settings or parameters to perform the fatigue testing. At the moment, I'm standing at the water hammer test. The water hammer test involves a large coil which generates a large volume of water. This water flows through this sample here, and at one moment the water comes to a sudden stillstand. There's a valve which closes, and due to the closure of the valve, this will generate a peak of 16 to 25 bar, and this is repeated over time. So some customers require to pass 100,000 cycles, and then the application is fulfilling the requirements set by the customer. So, but this is just one type of fatigue test, but there are more fatigue tests, and I will show you the next one. So here we are at the setup where we can test pressure vessels or solid state water meters, but then against a sinus or pressure over time, or a block wave pressure. So these are also fatigue tests which are required by our customers, and we can actually put different settings here for the upper and the lower pressure. So the way it works is that we have 25 samples at the same time connected to a pressure system which generates the sinus or the block wave pressure, and once the material fills or the application fills, it will stop only that sample which fills, and all the others will continue in the test. So in this way we can run 25 samples simultaneously without interruption. Yeah. So this is about fatigue testing, but it's also very important to understand the constant pressure resistance. And for that, I will move to the next setup. So constant pressure resistance, it's often called creep rupture or long-term hydrostatic strength. This involves that you expose the inside of an application or a pressure vessel with a constant water pressure, and you continue until the material or the application fills due to a phenomenon which is called creep rupture. And I will show you one sample. So the water bath is used as a medium for the temperature. So you can see a sample here. So what happens is that you could put a constant pressure on it, and at one moment it fills, and the filling mechanism is called creep rupture. And what's happening is that the filling mode also changes from ductile filling mode in the beginning, and if you continue for a longer time at lower stress levels, it will come to a slow drag road. And in the end, if the material starts to degrade, then you speak about degradation mode. But the last phase you never want to be in, because that means that your material would not be suitable for the water applications. Yeah. So with this, I come to the end of my live session here in the Water Management Center of Excellence, and I would like to hand it over to the next speaker.
Thank you, Eric and team. So you saw how much detail and depth we at SABIC go to characterize the materials, to generate the cards, and then to validate these cards, not only at the specimen level, but also at the application level with our Water Management Center of Excellence in Netherlands. So now the big question is how you, our customers, can get access to these cards. The first way is, of course, to get it through the Digimat material library. And you can see here that all the materials and the cards that we have in the Digimat material library. The second way is to get it through the material finder that we have in SABIC. Now, let me take a couple of minutes to talk about it. SABIC Material Finder is our one-stop shop for all of you, our customers, to find the right material for your applications. You can get access to this through our sabic.com website or by simply searching for SABIC Material Finder in Google. This portal allows you to quickly search and compare, evaluate our different material options that we have in our portfolio. You can use many easy-to-use search filters. You can search by features, you can search by industry, properties, even sustainability options as well. You can also search by free text. And we have a lot of case studies where you can get to know how our materials can help you in your application design. You need to register on this website to get access to the Digimat cards that we just talked. Registration not only gives you access to these validated material cards, but also helps you in other ways. You can select materials and make it as favorite materials. You don't need to go and search for it again and again. You can also get ability to contact us much more easier way by registration. And with that, we come to the end of our presentation, our session today. We are very much excited to collaborate with all of you, our esteemed customers. We will keep this QR code for a couple of, for a few seconds so that you can get access to the Metal Finder and can register. So with that, we all come to the end of the session, and I'll hand it back to Soumik. Soumik, back to you.
Thank you, Subhranshu, for wrapping up your session with such valuable insights on material availability in SABIC Material Finder. And a big thank you to all our presenters, Subhranshu, Vamshi, Prasad, Sebastian, and Eric. Thanks for sharing all your expertise and taking us through this comprehensive deep dive and unlocking superior predictability with validated Digimat cards. So your contributions have really, illuminated a great potential for these materials and applications for all the industry, specifically in electronics, mobility, infrastructure. I'm sure you all can appreciate the level of efforts and expertise that go into the validation of high quality material cards. And this session was to instill confidence in using material cards calibrated by an expert team behind that is there in SABIC, and use them for your simulations. Feel free to contact SABIC team for any support that you need. And for people who already know me, you know my coordinates. Please feel free to contact me if you have any further questions or doubts or comments. For the ever so talented team here, please let me know. We are now ready to transition into our Q&A session, where we are going to address your questions. We have received some fantastic submissions, and I think our panel is eager to dive in. If you have any additional questions about field grades or material validations or specific applications in your industry, please submit them via the Q&A chat now. It will keep coming in. We're trying to do our best to cover as many as possible. But before we start, a quick reminder, this webinar is recorded and we will be sharing the recordings very soon on demand. Now, I think we are ready to get to your questions. Here is your first one. Okay, so one is, why is the tensile strength and Young's modulus values not matching with the 0-degree test data and from technical data sheet? What could be the reason? So I'm not really sure which slide is this referred to, but if experts, I think Vamshi, this is yours. If you can address this.
Thanks, Soumik. Yeah, so that's a very good question, right? So as you can imagine, when you injection mold in a tensile specimen, directly injection molded tensile specimen, you can establish that the fiber orientations get really well aligned. Whereas in a shear plaque, it is a much wider width of flow, so you do not expect such a well alignment of fibers, right? And also the processing conditions do vary, right? The shear experience do vary. So our experience has been that in directly injection molded tensile specimens, you get much higher alignment than even the 0-degree cut specimens. So in real world scenarios, if you were to really look at it, I would say 0 is your best performance, measure, and 90-degree would be your worst performance measure for a tensile behavior, right? And directly injection molded is even overestimating it than what is possible in real world. That's how I would put it at. I hope that answered the question.
Thank you, Vamshi. All right, so here's the next one. How do we account for different thicknesses in material cards for real parts? So I think that's the question for you again.
Yeah. Again, a very good question, a solid question. This was something that I was plagued with when I started this whole journey of calibration and going into these workflows, right? So like I mentioned, there are 2 steps to this. The first step is to be able to account and predict fiber orientations using filling tools. That is where the different thicknesses, accounting for different thicknesses and being able to capture in different thickness geometries, fiber orientations accurately improves the predictability in real world part geometries, right? Not really coming from the Digimat material models. So Digimat material models, if you give it a set of fiber orientation, it does the micromechanic studies and predicts what will be the local behavior. That's what the Digimat card does. But what the processing tool does is predicts for different thicknesses how that orientation is going to be. And that is very important to be calibrated in the fiber filling solvers and not from the Digimat material cards per se. Yeah.
Okay.
I hope that answered the question.
So, okay, so we have not much time left, but there are quite a few questions. I'll try to address them as soon as we can. There's another question for hybrid materials, plastic plus metal. How do you simulate testing and generate Digimat card? So, I mean, I think that is for real parts, Molly.
Yeah, for the hybrid applications, hybrid parts where you are metal and plastic, both are there, like overmolding things, we do application level testing. But when you're talking about thermoplastic composites, either the glass fiber or carbon fiber is within the material, and that's what we covered. But when we have this hybrid structure at an application level, we have application level testing to really characterize the, at that application level.
Okay, thanks, Supranshu. I think the next one is for Sebastian. What is the typical sample size for a CT scan? And what are the factors that are most important for high quality CT data?
All right. So there's very strong correlation between the resolution that we want to achieve and the size of the sample. As higher the resolution is, the smaller the field of view is, and the smaller the sample should be. Typically, if I use a resolution of 40 micrometer, I can scan a sample of 10 centimeter. If I use a resolution of about 3 micrometer, I can scan a sample which is about 12 millimeter. And if I want to achieve some pixel size which are below 500 nanometers, then we are talking about samples which are in the millimeter range. The second part of the question was about the parameters, which are really important to take into account to have a good scan, right? So there's the contrast is very important. So this we adjust with the X-ray. We need then to optimize the exposure time. to have a signal which is strong enough, but that the camera is not saturated. That's really the two major important parameters. And then we can play as well with different settings like the number of average of frame, the number of projections that we take to limit the artifact and to achieve better resolution. In glass filled material, for instance, in order to limit the artifact due to the scattering of the glass fiber, I typically use 6,000 projections. One thing to have in mind here is the higher the quality is, and the higher the number of average is, the number of projection is, then the scanning time is drastically increasing. And we can go to few hours of scanning time up to few days of scanning time. So it's also always kind of a threshold optimization between the resolution, the size of the sample, the quality of the images, and the time that is needed for the scanning.
Okay, thank you, Sebastian. There are a few more interesting ones. If it's okay, I think let's extend this by a few minutes, if not everyone doesn't mind. Okay, so this is a touchy one. I would like to ask this first. We are using Digimat. Do you host most material cards on Material Finder, or do they also make it to Digimat MX? Subhranshu?
So, yeah, we host all our cards on the Digimat library. So in the Digimat library, we have some cards directly accessible like the elastic cards, and some are on request, but you will get to know all the cards that we have. Okay, so the same thing is also available in the Metal Finder. But Metal Finder has not only the Digimat cards, but you can also get other solver cards, right? So Metal Finder is our one-stop shop, like I mentioned, for all sorts of multi-point metal data, technical data sheets. You have CE cards, including Digimat cards, as well as our product collaterals and marketing collaterals, application case studies. So if you are looking for Digimat cards, you can either choose SABIC Metal Finder or Digimat Metal Library, but SABIC Metal Finder has more than Digimat cards in it.
Sure. Another interesting question. More number of layers is used to calibrate the fiber orientation, but in real life application, we can't use such high number of elements through the thickness. How do we handle that?
Yeah. Again, really nice question, right?
Very nice question.
Yeah. And this is again a very true and pertinent question. So depending on the fidelity that you want to achieve in your modeling, right? You want to predict something really accurately in certain regions. I would say the learnings are use more layers of mesh to the thickness. If it's not possible, I'm not a mode flow guy, but if it's not possible to do it locally, so it's again, like Sebastian also mentioned, a trade-off between accuracy and time that you want to spend in simulation. So you can take that call, but be aware that very coarse layers to the thickness would lead to inaccuracies. And as a minimum thumb rule in structural mesh, 8 to 10 integration points to thickness. Otherwise, you're not going to capture the center core randomness and the skin effect. And similar, at least 12 to 16 minimum layers to thickness for the mold filling simulation. Anything lower than that, you are like way off. So, and then anything above that, yeah, you go to accuracy levels. That's
typically in terms of mesh density through the thickness, we aim for at least 3 to 5 layers through thickness at least for a second order dead mesh. So that's the thumb rule that we have at least internally for most involved parts, right, Vamshi?
Yeah.
Perfect. Okay. Many questions, really interesting ones. But a couple of them for Eric. I've consolidated 2 of them. One is, what is the purpose of the hot water exposure test? To what extent it simulates the real world usage scenario? What are the pressure wave intervals applied in the water hammer test? Probably the frequency. Another person asked, like, what is the level of frequency of fatigue tests on these pressure samples?
Yeah.
I know these are 2-3 questions at a time, but if you want me to repeat at any given point in time, please feel free to do so.
Okay, let's. You can hear me hopefully. So the first question about the exposure of the tensile bars for the hydrolytic stability. So what you want to achieve is actually you want to understand if the part during its lifetime, because it will see water and temperature, that the material does not start to degrade over that time. And for that purpose, actually, we expose tensile bars to different temperatures. So let's say 60, 90 degrees, and we can even go to higher temperatures. And what we measure is actually the properties as a function of the exposure time. If you do that, then you have also a good understanding if the material can withstand during its lifetime the water and the temperatures without showing a degradation or a severe degradation. So if you have a material which shows a very severe degradation during the lifetime and the temperatures which the application sees, then you know this is not a good material for this application. So you really make the first step on choosing the right materials before you proceed with, even with the predictions and the validation testing later on. Then the next question was about the water hammer. The problem with the water hammer is that, the equipment is such that you can actually program the way the test is executed. So what we see is that we have customers having different requirements. So that means that one customer can ask for instance, for a water hammer test that the peak is within 0.02 seconds, for instance. So you need then to program such that you can achieve that. One customer is, for instance, asking for a 16 bar. Other customers can ask for 25 bar. So it's really driven by what the customers have as qualification testing in-house for their application. And the way we have set up here the laboratory is such that we try to cover as much as what we see by the qualification tests of our customer. So the equipment is built such that we actually can choose the parameters which matches with the requirements set by our customers. So hopefully that answers the questions.
Yeah, and there was another question. I think that was a bit of a follow-up and should be applicable. It's not specifically mentioned, but I think the question is for you, Eric. Are these tests also performed on non-reinforced plastics?
Yeah, that can also be performed on non-reinforced plastic. So you can have any application also without fillers and do the same tests. But we know for some materials that we apply fillers to improve some of the performance, like fatigue. We know that some materials, if you add fibers to it, that you increase the performance. But yes, you can also perform the test on unreinforced materials. That's no limitation on that.
All right, we'll take one last question. So, although there are many in line, and I would like to thank to the audience for asking so many questions and really quality ones. But I think we have time to take one more. But do not worry if you have not addressed your queries here. We're going to reply to you over an email. And of course, we saw a lot of chats wherein the request for sharing the recordings have been put. But here's the last question for today. Are long-term material properties like fatigue, creep available for all material grades? If not available, what is the typical lead time to perform these tests and made available on Material Finder or Digimat MX?
You can take it.
Okay. So typically, as you can expect, creep and fatigue typically take quite a bit of time, depending on the duration of the test that you require, right? So for instance, if you need a pre-test over 5 days, it takes 5 days to run the test, right? So the duration of the test determines the overall lead time of the experimental program. Fatigue, relatively speaking, takes lower time, but still is more time expensive in terms of time as compared to a uniaxial tensile test. Typically, our lead times could be anywhere from a few weeks to a few months. That would be our lead time for once a customer requests for the data. And again, it depends on the conditions that the customer wants the data for. Anything you want to add, Subhranshu?
Yes. Yeah, thanks, Prasad. To add to that, to your first question, yeah, we have a lot of materials for which creep and fatigue cards are available already. For those materials that is not available, what we would like to do normally is to really sit down with our customers to understand the requirements, because creep and fatigue are very time consuming, expensive test, and we want to really serve our customers the best way. So we want to understand your application requirements, what are the temperature range, what is the stress range, and what are the other conditions that your application will see. So together we would like to understand the requirements, plan the test, perform the test, make sure that the cards are generated properly, and also we can do validation as much as we can. So it is actually a collaborative effort. So if you want to generate something which is already not available in Digimat library or SABIC Metal Finder, do contact us. We can have a call to understand the requirements, and the lead time will depend upon how many conditions, how many stress ratios, how many stress labels, or how many other conditions like R ratios you need the data. So it depends from condition to condition.
Thank you, Subhranshu, and we have some chat, comments about this webinar. I think well organized and coordinated webinar session, and I'm sure it was. Thanks a lot, Prasad, Vamshi, Subhranshu, Sebastian, and Eric, for your valuable time and insights into material testing, validation, and whatnot, being patiently here answering every question, as many questions as we could answer. But it's not ended yet. We are going to get in touch with you for the questions that we have not been able to address in this session. And with that, I'd like to thank all the audience for being patiently here for the extended time and being with us, extending a patient hearing to this deeply technical session. So thank you again, everyone. Thanks for the wonderful session.
Thank you.
Thank you all.